Good morning, quantum enthusiasts. Welcome back. We're really going to do it this time. In the next few lectures, we're going to see an efficient algorithm for a quantum computer for solving the problem of factoring positive integers. So this is the most famous algorithm in quantum computing. Because as you know, for like most of the last 50 years, almost all of theoretical cryptography was predicated on the belief that there's no efficient algorithm for factoring into prime factors like really big numbers, like 1,000-digit numbers. And indeed, there is no known classical algorithm that can factor like 1,000-digit numbers, let's say on a supercomputer, in less than like 1,000,000 trillion years. But then in 1994, it was shown, well, that with a quantum computer, you can do it real fast. So with a quantum computer, this is what we're going to see in the next 3 lectures. You can factor n-digit numbers in something like n-cubed steps or quantum instructions. In fact, if you're really a hardcore theorist, you can kind of get this down to basically order n squared, but it's like one of those things where you have to use an extremely sophisticated algorithm where like the constant factor is like so bad that you'd rather just use the algorithm that's order n cubed time. Okay, so that means if n is like 1,000, which is like a super hard case, this would be a billion. Okay, so if we can just get like quantum computers that can execute 1 billion steps, maybe right now they can do like 1,000 without breaking down, then we can solve this fantastic problem. So this was first proven by Shor in 1994, and maybe the key ingredient in his algorithm was the quantum Fourier transform, which we didn't talk about in this class. As I mentioned, then later, like a year later, this other person, Kitaev, came up with an alternative algorithm for quantum factoring, where the central ingredient is this rotation estimation routine, which we did do a lot of in this class. And that's the algorithm we're going to follow. I mean, if you squint at it really closely, you will eventually see that they're actually the same algorithm, but from very different perspectives. So I prefer this perspective with rotation estimation, partly because that subroutine is also useful for Grover's algorithm and lots of other quadratic speedups. Okay, so this is a problem about a number theoretic problem, taking two like 1,000-digit or like a 1,000-digit number and trying to factorize it into like 2, maybe 500-digit prime factors. And to fully do all the details, you need to do a little bit of elementary number theory. But this is a course about quantum computing, not about number theory. So I'm going to try to like gloss over the number theory stuff as quickly as possible so we can get to like the quantum component of this algorithm. And I intend to like cram it all into like, I don't know, the second to last lecture, where we'll just have like a number theory lecture for fun where we tidy up all the number theory details. So I am going to like skip over these steps a little bit, but we'll come back to them. Okay, so what is the task in this problem? Well, your goal is you're given a number which we'll call capital N. And think of it as like, I don't know, thousands of digits. Okay, so you cannot store this. If this were a classical problem, you cannot store it like in like an int or something on your computer. Like you have to store it as like a string. This is like 1,000 digits. And you just want to output its prime factorization. And we're going to make a simplifying assumption for this exposition of the factoring algorithm, which is not really a big deal, but we're going to assume that it just has 2 prime factors. So we're going to assume that n is p times q, where p and q are odd primes. And this is just to make there be like a little bit less bookkeeping and a little bit less number theory. You can rest assured that like the quantum factoring algorithm can handle like literally any n that you give to it. But for simplicity, we'll just focus on this case. Anyway, this is like intuitively the hardest case because, as you may know, like you can check if a number is a prime efficiently. So that's not a problem. And like somehow like the more prime factors there are, like the easier they are to find. Moreover, this is the case that arises in cryptography, like an RSA. You're always picking like an n, which is a product of 2 primes. So this is both the hardest case and like the most interesting case. Okay, so I will now tell you the algorithm. Well, I'll tell you the overview of the algorithm. So here it is. I should say it's kind of like a hybrid classical and quantum algorithm. So there'll be like some quantum stuff and some classical stuff at the beginning, at the end. The main quantum routine will be, as mentioned, this rotation estimation, but there'll also be like classical stuff mixed in. Okay, so this is the overview of the algorithm, and step one is the hardest step, as we'll see. So it's this: find the smallest number L such that 2 to the power of L is equal to, or congruent to, if you like, 1 mod n. Okay? So you're trying to find the smallest power of 2 that gives 1 as a remainder when you divide by n, the number you're trying to factor. And this is this is the heart of the algorithm. This is the complicated step. I say find. Well, it's going to be not so easy to do this finding task, but we'll come to it. And then the last two steps are not hard. And in fact, you just do them on a classical computer once you find this L. This L itself will have like 1,000 digits. And you just do this. You let x be 2 to the power of L divided by 2 mod n. Okay. And then 3, here's the output. You output the GCD, greatest common divisor, of x minus 1 with n, and also the greatest common divisor of x plus 1 with n. Okay, that's it. That's the whole sketch of the algorithm. I should add sketch. Okay, so the major question, and this is the major issue that we'll work on today and actually mostly next time, is how to do step 1 efficiently. Okay, this is the part that we're going to need a quantum computer for. As I hope you recall, steps 2 and 3, you don't need a quantum computer for. You can do them efficiently on a classical computer. You'll have to remember back to your 251 days when you're talking about RSA and stuff. I'll come back to this in the number theory lecture, but this is modular exponentiation. You do this by repeatedly squaring and then always taking mod n. So you can do this efficiently when L and n are thousands of digits long. And GCD, this is also an efficiently solvable problem with Euler's algorithm. You do this. Well, you remember Euler's algorithm, maybe. So you can compute this efficiently when they're like 1,000-digit numbers. Okay, so again, we'll come back to that later if you need a refresher, but hopefully you know that already. So the main question is how to do this one. Now, before we get into it, let's do some examples to understand why this might work at all. Okay, so let's see how this algorithm works. So we'll do an example. Literally, the smallest possible example is n equals 15, because, as I said in words, we're going to assume that neither of these is 2, because that case is easy. Or maybe you should also assume that they're different. So it's like p and q are different primes. So the smallest example is 3 times 5. So imagine you didn't know how to solve factor n equals 15. It's only a 2-digit number, but well, there you go. So if it's such a small number, we can just literally do this by hand in the dumbest possible way. So the dumbest possible way is to start computing the powers of 2 and then checking to see if they're congruent to 1 mod, the number you're trying to factor. This is not a good idea in general. If L has thousands of digits, this would take you like 10 to the 1,000 trials, but when it's 15, it's fine. So we're like, okay, well, there's 2, and then there's 4, and then there's 8, and then there's 16. But 16 is 1 mod 15. And hey, we're already done. We found it. This is the smallest power of 2. That's congruent to 1. So that means L is 4, because this was 1, 2, 3, 4th power. Okay. That means this x is 2. And so then we compute, Oh, sorry, not x is 2. L over 2 is 2. So x is 2 to the 4 divided by 2, mod 15 if you like. But that's 4. Okay, so x is also 4. So then we compute the GCD of this plus or minus 1 with the thing we're trying to factor. So 3 and 15. And we also compute the GCD of 5 and 15. This is a very simple example. And hey, this is 3. This is 5. And so we did it. 15 is 3 times 5. Great. Okay. Let's do like the next smallest example. The next smallest example is n is 21. So if you don't know the factors of 21, then prepare to learn them. Okay, so we'll do this step again, like super slowly. So we'll do 2, and then 4, then 8, then 16, then times 2 is 32. Now 32 is the same as 11 mod 21, and then we double 11, and we get 22. But hey, 22 is equal to 1 mod 21. So we stop. We found it. And this was like the 1, 2, 3, 4, 5, 6th power of 2. So therefore, L is 6. And so x is 2 to the power of 6 divided by 2 mod 21, which is 2 to the 3, which is 8. Okay, so then we compute the GCD of this plus or minus 1 with n. So that's a 7 and 21. And the GCD of 9 and 21. Okay, that's 7. That's 3. So we did it. 7 times 3 is 21. Okay, so that's an illustration of it working. Of course, you should be doing this with like thousands of digits. Okay, now I wrote here the major issue is how to do step 1 efficiently. There's actually 2 minor issues, but these are very minor issues, easily fixed. But I'll bring them up. So minor issue 1 for this algorithm. Slightly slipped it past you. Like, what if L turns out to not be even? Because this algorithm tells you to, like, compute L divided by 2. And if that's a fraction, then that's like weird in modular arithmetic, and this won't be an integer. So actually, it's a problem. So if L turns out to be odd, then this algorithm as written fails. But we're going to come back to it in a second. There's an easy way to fix this. So don't get too stressed about that. OK, so there's also a minor issue 2 that we'll come to when we see a little bit more about why this algorithm should work. So here it looked like, was this like a miracle? Like, what happened here? So let's see what happened here. So why might this algorithm actually work? OK, so you somehow find this L, such that the Lth power of 2 is 1 mod n. And then you cook up this x. And now let's look at x squared. So, OK, x squared is 2 to the L over 2, assuming that makes sense, squared. OK, we have exponents, so that's 2 to the L. And that's, this is all mod n, by the way. And that's 1. That's the whole point. X, it's 1. OK, so that means that mod n, x squared minus 1 equals 0, just rearranging. OK. And then we can factor this. So that means x minus 1 times x plus 1 equals 0. This is all mod n. OK, so that means this is a multiple of n. This is divisible by n, which remember, OK, I didn't write it, but it's p times q. OK, so n only has 2 prime factors in its prime factorization, p and q. And now this is a multiple of n. So this also has p and q in its prime factorization. OK? I always have to remember how to say this carefully. So p and q are in the prime factorization of this. And therefore, by the nature of primes, like p has to appear as a prime factor of either this one, or both. And similarly, q has to be in the prime factorization of either this one, or that one, or both. Now, it cannot actually be both, because let's say p divides x minus 1 and x plus 1. Then it divides their difference, which is 2, which is not possible if p is an odd prime. So p is a prime factor of exactly one of these two. And also q is a prime factor of exactly one of these two. So let me write that. P is a prime factor of exactly one of x minus 1 and x plus 1. Same for q. Okay. Now, it could be that you're like, oh, P has to divide one of these two. Maybe it divides x plus 1. And Q also has to divide one of these two. Maybe it also divides x plus 1. That's a bad case. So that's actually minor issue 2. What if P and Q both divide into x plus 1? I'll explain why that's a bad case in a moment. It would also be bad if P was a factor of x minus 1 and Q was a factor of x minus 1. Actually, that cannot happen. I'll leave that as an exercise for you. Or maybe we'll eventually get to it. Why can it not be that both P and Q divide x minus 1? Has to do with the minimality of L. Okay, but if this doesn't happen, they don't both divide x plus 1. Then it has to be that like P divides one of them and Q divides the other, but remember they only divide one each. So I always have a hard time like expressing this carefully. Let me write over here. Because the point is that if neither of these minor issues happens, then the algorithm will work, and we'll get the prime factors, which are P and Q. So if the minor issues don't happen, then we get something like P divides x minus 1, but not x plus 1. And Q divides maybe x plus 1, but not x minus 1. Or it could be the other way around, but that's just interchanging the roles of P and Q. And then in that case, step 3 will work. So that's a great case, because then what's the GCD of x minus 1 and n? Well, n only has two prime factors, P and Q. So this GCD is either 1, P, Q, or P times Q. But P divides it, but Q doesn't divide it. So this would have to be P. The GCD of x plus 1 and n similarly, n only has the prime factors P and Q. Q does divide x plus 1. P doesn't divide x plus 1. So this would have to be Q. So again, happy face. When we compute the GCD, we get the two prime factors. Okay. So let me end this segment by saying either one of these minor issues can happen for the number you're trying to factor. They actually tend not to happen. If like n was chosen to be like a product of two random primes, then usually neither issue happens. But they can happen. But there's a little trick for evading them. So we're going to see this trick only later when we do the number theory lecture. But I don't know, in later lecture, when we do some number theory, we'll see that both of these minor issues are easily fixed by doing the algorithm with some bases, I'll say b, other than b equals 2. And let me explain in words what I mean. Here's what I mean by base 2. It's this number here. If you actually look at our justification for everything, it didn't actually rely on the fact that this number was 2, that we were computing powers of 2. Because like this was the whole explanation for why it should work right here. And if this was like 3 instead of 2, it would be the same explanation. So you can always try this algorithm with 3 instead of 2, or 10 instead of 2, or your favorite number instead of 2. And if you try it with different numbers, let's call it b, then you'll get like different values of L. And then you'll get, and that, you know, if the first number you tried it with 2 made L odd, then maybe the next base you'll try it with will make it even, and you'll be happy about this minor issue. And then, like, you also get into a situation where, like, you know, this may or may not happen depending on what the base is. And it's a number theory fact that if you just try like a few different random choices in place of 2, then after a while, with high probability, you'll get over both of these minor issues. Okay, so nevertheless, we'll maybe deal with that later, and we'll just only worry about the case where this space is 2 for simplicity, just remembering that you can fix these issues by changing that to a different number, if you need to.